Welcome to the UGC lecture series. This is the EPG Pathshala lecture series on computer science, and here we are talking about data structures. Now, in previous two modules on stack, we had discussed stack and its stack ADT in general and stack implementation of using arrays, linked list and ADT list. Now, as we already discussed in the first module on stacks, we said that stack is a very favorite data structures of computing. So, in this and the next module, we are going to take some typical and interesting applications of stacks that is used in the computer science area itself. So, that is what we are going to do in the next two modules. So, in this module, we will look at an important, very important application of stack, which is to do with algebraic expressions. So, here these are the people associated with creating this module, and the learning objectives of this particular module is to discuss some important applications of stacks, but here we are actually looking at only one area of application, which is algebraic expressions. So, the use of stacks in algebraic expressions. I will tell you later on why this is very important, and then we are trying to outline the conversion of infix expression to postfix expression using stacks, and then we will explain about the evaluation of postfix expression using stacks. Now, let us just have a small recap. The stack is the simplest of all ADTs. So, understanding how a stack works is quite trivial, but the application of stack, however, and its implementation is not so much, because the important thing is how do you create a design which allows the use of a stack. So, you must catch that point that that particular application requires the use of a stack. So, we are looking at many applications, reverse polish or the postfix, parsing, function calls and so on. So, application stack, one is the call stack, the recursion, searching networks, traversing trees. So, basically stack is used to keep a track of where we are. So, example that we are looking at here is evaluating algebraic expressions. We can also look at checking balanced expression, recognizing palindromes. So, that is a trivial problem, so to say. Some of these applications are the core of how a computer is implemented itself, and that is why stack is very important. Here in this particular module, we are concentrating only on one particular area of application, and that is algebraic expression. We will be talking about infix to postfix conversion and postfix evaluation, and as we go along I will tell you why this particular area has been has been dedicated, a complete module has been dedicated for this. So, let us look at algebraic expressions. Now, algebraic expressions can be of three types basically: infix expression, prefix expression and postfix expression. Infix expression, all of you know right from school days, this is the type of expression that we use where the operator appears between its operands. Just to recall, these are called as operators and these are called as operands, any operator, any operands. Now, prefix expression, an operator appears before its operand. So, this is equivalent to this, and postfix expression, an operator appears after its operands. Now, when you just look at it as a surface level, what is so great about this? After all, the way you represent the expression is only changing. As we go along, we will see why it is different. So, and in infix expression, now I am just looking at an infix expression. If you look at the postfix and prefix expression, there is no question of parenthesis, and also the inbuilt precedence that we need is already taken care of in the postfix and prefix expression, and that is why the postfix and prefix expression is important. Most probably they will most cases they use postfix, they do not use prefix, but you can also use prefix, but postfix is most commonly used. Now, let us look at what happens here. Now, if you take this, if you take an infix expression, it has some precedence rules. We are so used to it because we have been doing it from childhood days that we forget that there is a precedence, but there is. So, if you look at a plus b star c, b star c b into c has to be done first before a can be added to it. Okay. And of course, brackets has to be taken care of first. So, what the order in which the operations are done in this particular case is d into e is done first, then f is added to it, that is left as it is, then b star c is done next, okay, and then this expression into g is done next, then you do the addition of a and the addition of this part to this part. So, there is a particular order. So, 1, this operation first, this operation next, this operation third, this operation fourth, this operation fifth, and this operation sixth. So, star is given higher precedence than plus, within brackets is given higher precedence than anything else, star is given the next higher precedence, and then the other plus and minus operations. In fact, exponential has the highest precedence, and then of course, the other order is left to right. Now, if you look at this, this is the reverse polish or the postfix expression, both are the same. So, here if you see D E is done first, then F is added to it, then B C star is done next, then this expression G star is added, multiplied, then A is added to this expression, and this expression is added to this expression through this plus. Now, if you are doing this, again D star E is done first, then F is added to it, then B star is B C star is done next, then G is multiplied to this, okay. Then then A is added to this, and this part. Please note these will be values, we will see that also as we go along, is added. So, this is the important. So, what have we done when we are doing postfix and prefix, or we will just talk about one, they are synonym, they can be, both are the same, both are similar, both are the characteristics are the same. So, in the postfix expression, both the parenthesis is taken care of, the precedence is taken care of, and the left to right ordering is also taken care of automatically. Actually, not automatically, when we are converting from infix to postfix, that is taken care of. So, prefix and postfix expression do not need precedence rules, do not need association rules, and do not need parenthesis. They have simpler grammar expression, they have straightforward recognition and evaluation algorithms, and that is why postfix expression is used as a basis for the computer to do calculations. And that is why I said that algebraic expression, we are dedicating a complete module to algebraic expression, because it is a core of how expressions are evaluated using a computer. So, let us go to the as I told you, prefix is not normally used, it is postfix that is used for convenience sake. So, reverse polish or the postfix expression is what we will first talk about. So, alternative reverse polish notation or the postfix notation, alternative you can place the operands first followed by the operator. So, here you have so this is in brackets. So, 3 4 plus, then 5 into 6 minus. Passing reads left to right and performs any operation on the last two operands. So, you do this, you see this operation is done first, you get a 7. Okay. Then next you see this, you put it in the then multiply, you do this operation. So, you get 35, then you see 6, then you do this minus operation. So, this is the order in which the operations are done. Now, reverse polish notation, this is called reverse notation after polish notation after the mathematician Jane Lukai-Sievers. As you can see, this forms the basis of the recursive stack used on all processors. He also made significant contributions to logic and other fields. So, this is the person who is responsible for this reverse polish notation. Now, the benefits of reverse polish notation, no ambiguity and no brackets are required. This is the same process used by a computer, this is very important, used by a computer to perform computations. Operations must be loaded into registers before operation can be performed on that. Operands must be loaded into registers before operations can be performed on them. That is why polish, the reverse polish is more important than prefix. So, operands are loaded, that is the way, that is the natural way in which postfix expression or reverse polish expression gives the expression. So, the reverse polish can be processed using stacks. Okay. So, reverse polish notation is used for with some programming languages like PostScript, PDF, HP calculators. Similar to the thought process required for writing assembly language code, you cannot perform an operation until you have all the operands loaded into the corresponding registers. That is the way in which assembly language is done. Load A, load B, add AB, so that. Now, when an ADT stack is used to solve a problem, the use of ADT's operation should not depend on its implementation. This is what we were talking about before also. So, we are going to look at how to evaluate an infix expression. There are two steps involved. First is converting the infix expression into a postfix form and then evaluating the postfix expression. So, these are the two steps that we will be doing in this. So, first let us look at how to convert an infix expression to a postfix or a reverse polish expression. So, when you are converting infix to its equivalent postfix expression, the facts about converting infix to postfix, what we have to think about is operands always stay in the same order with respect to one another. So, that does not change. An operator will move only to the right with respect to the operands, it cannot move to the left. All parentheses have to be removed. So, there are 3 steps: operands always stay in the same order, the operator will move only to the right, never to the left, and all parentheses have to be removed. So, operands are in the same order, operators occur later. Strategy: send operands straight to output, send higher precedence operators first, if same precedence send in the left to right order, hold pending operators on a stack. So, now comes the application of stack for converting from infix to postfix. So, what you are doing is, if you have send operators means you are sending to the output. So, if you have lower precedence operators, you will have to pending operators, that has to be put on a stack, and that is where we are using the stack. So, the steps for converting from infix to postfix, for before we go into this, for us to do this algorithm, you need certain precedence information, and there are 2 types of precedence information we will be talking about. I will talk about that. So, step 1, scan the infix expression from left to right for tokens. There are 3 types of tokens that can happen in this infix expression. One is operands, one is operators, and the third is parenthesis. Parenthesis, again you have left parenthesis and right parenthesis, and perform steps 2 and 2 to 5 for each token in the expression. So, you have 3 types of token. If token is an operand, append it in the postfix expression, that is directly send it to the output. If token is a left parenthesis, you have to push it in the stack. I will come to this later again. Step 4, if the token is an operator, okay, pop all the operators which are of higher or equal precedence than the incoming token, and then append them in the same order to the output expression. After popping out all such operators, push the new token into the stack. Now, this is the most important and the most interesting step in this whole. So, what you take? You have an operator. Now, this operator has 2 type of precedence. We have not defined that exactly here. We are just saying higher or equal precedence. So, what you take? You take the incoming operator, check with the operators that are on the stack, and you pop all. Remember, the stack contains only operators. Operands are always pushed to the output. So, check all the operands on the operators on the stack, and pop all operators which have higher or equal precedence than this incoming operator, and then push it out to the stack in the same order in which it has come, and then after popping all such operators that have been on operators that have been on the stack, this particular incoming operator is pushed onto the stack. So, that is the operation. Now, if right parenthesis, now you have open parenthesis, push it on the stack. If you have a right parenthesis, you pop all the operators on the stack and append it to the output till you encounter the open parenthesis. Okay. Pop the left open parenthesis, but do not push it to the append it to the output, because as you know, postfix expression does not have a parenthesis. The final step, when all tokens of the infix expression has been scanned, all the elements that are left on the stack is immediately popped out in that particular order, put in the output string, and so what you will have in the output is a postfix expression. So, this is the conversion from infix to postfix. To understand this better, we will go for an example. Okay. Now, I told you that there are 2 types of precedences. Now, one precedence is called the incoming precedence, that is the incoming, that is before you put onto the stack from the infix expression. What, when you look at a operator, operators only have these precedences. So, you look at the operator, that is called the incoming operator precedence or incoming precedence, ICP, and you have something called ISP, that is the precedence of the operator when it is in the stack, and that is called the in stack precedence. So, you have 2 types of precedence, incoming precedence and in stack precedence, that you remember. Now, with that we will go initially. Now, this is the infix expression. So, okay, and initially stack is empty. Now, look, remember what we are doing this for understanding an application of a stack, okay, ADT stack. Okay. So, stack is empty, we only have the infix expressions. Now, this is just to tell you the crux of this particular step. So, what it says is operators are taken of the stack as long as its in stack precedence ISP is greater than or equal to the incoming precedence ICP of the new operator. So, you see an operator here, if whatever is here inside in stack precedence higher or equal to this, you keep popping out, that is what it means. So, initially top is done. So, here we have called the create stack operator, and a stack has been created. Now, we have to read. So, the first token that we read is A, which is an operand. Now, according to the algorithm, the operand is appended to the output as it is. So, A is appended, finished. So, next that is the infixed. So, next you have the next operator that you have is star or multiplication operator. Okay. So, next token is multiplication operator, stack is empty, and it is pushed on to the stack, because if the stack is empty, then there is no question of precedence or anything popping. So, you just push it on to the stack. So, you have now called a push S comma multiplication operator. Yes, if you call S is the stack. Remember, the postfix does not change. This is the second step. Next, what you see, the opening parenthesis is what you will see. So, next token is open parenthesis. The incoming remember, we have two precedences, ICP and ISP. So, the incoming precedence ICP of the open parenthesis is maximum, and when another operator is to come on top of it, then in stack precedence is the least. Okay. So, infix, so what you see, because its incoming precedence is the maximum, you push it onto the stack. So, that is over. Next you will have B, we will see that, and the top has been incremented. So, again you are using a push stack. So, you just, when you see an operand, nothing you have to do, you just append it to the output. Next you see a addition operator, okay, addition operator. So, now you will have to, next token is the addition operator. The in stack precedence ISP of open parenthesis is the least. So, you do not have to push it out. Remember, you have to push it if it has higher precedence. Now, you do not have. So, this addition operator is just pushed onto the stack. Again, we are calling push stack. Okay. Next, what you see will be C. So, that will be appended as it is C. Okay. Next, what you see is a close parenthesis. Now, close parenthesis means that you pop all the elements in the stack till you reach the open parenthesis. Just remove the open parenthesis, but do not append. That is the step. So, what is the operation you do now? You have to pop. So, what you do from this, you see the close parenthesis, what you do, you just pop out till you reach this. So, you pop out the plus, that is all. The open parenthesis is not appended. Now, you have minus D slash E. Now, minus is a operator. So, what you will have to do, the next one, minus an operator, the ISP of star, okay. No, this is star, remember the multiplication operation, the in star of that is higher than minus. So, we have to pop that star, okay, that star, and input the push the minus. So, you have done a pop and a push together and append it, and this is pushed. So, you pop it out, append it to the output and push in the minus. Now, next what you see is the D. D is just an operand, so just push it on the stack. Okay. Next what you see is a division sign. Now, division has a, we will insert division as it is, because it has a higher precedence than this. So, you do not have to pop this out. Okay. So, stack, because its precedence is more than that of minus. So, you just push it on top of the stack. Now, what you see is E. So, output the E as it is. Then you have to empty the stack in the order in which it is there. So, in the order in which it is last in first out. So, this will come out first and this will come out. So, this is the final output that we get. This is the running example of infix to postfix. So, that is the pseudocode as well as the operation. As you have seen, you have used only 3 things: the create stack, the ADT stack that we will use for this infix to postfix conversion. We will just need an create stack, push an item into the stack and pop an item. Okay. And the pop item, you need the item because you have to put it in the, append it to the output to form the postfix expression. Once the postfix expression is formed, we will have to do the evaluation of the postfix expression. So, that is the next one. So, when you are doing the evaluation of the postfix expression, again we are going to use the stack. So, whenever an operand is encountered, you push it onto the stack. Whenever an operator is encountered, remember in the postfix expression you have only two type of components. One is the operator, the other is the operand. There is no parenthesis because we have removed it from infix to postfix. So, whenever an operator is operand is encountered, you just push it onto the stack. So, the opposite of what we did then. Whenever an operator is encountered, you pop the required number of operands from the stack, do the operation and evaluate it and push it back onto the stack. Here the number of arguments that have to be removed from the stack depends on the type of the operator. Most cases it will be binary operator, but if it is a unary operator, for example exponential or unary minus, then only one operand has to be popped out, the operation has to be done and that has to be returned to the stack. But here in this example we will be mostly talking about binary operators because that is a little more interesting. But remember, how many elements have to be popped out of the stack depends upon the it depends only upon the operator. If it is a binary operator 2, if it is a unary operator 1. Okay. So, this is the algorithm, empty the operand stack, create the stack. While there are more tokens, get the next token. If the first character of the token is an operand, push it onto the stack. Else if it is an operator, pop the right operand off the stack, pop the left operand off the stack, evaluate the operation, push the result back onto the stack, pop the whatever is inside the stack, finally we will get the result. So, let us take a running example again here. So, this is the postfix expression that I have. It is a big expression 3 6 plus 5 5 6 into plus 8 multiplied minus 8 6 multiplication plus plus. Now, when you see an operand, you push it onto the stack. Okay. So, next also you see a operand only. So, push it onto the stack. Next also you see an operand, push it onto the stack. Okay. Now, next what you see is an operator. Okay. So, you see the operator. Now, when you see the operator, you have to pop, when you see the operator, you have to pop the first two elements, I mean the last two elements, top two elements, two elements because it is a binary operator. You have to remove those two elements and do the operation and push the result back onto the stack. So, I call this as, I put a notation here as 1 to say this is the first operator that we are encountering. So, what has happened is you would have these two which were on top of the stack has been added, the result has been put here. So, this is the plus operation, the first this notation here and 9. So, pop 3 and 6 off the stack, do the operation plus and push the result onto the stack. So, in one look at an operator, you are doing 2 pop operations and 1 push operation. 2 pop operations because you are, it is a binary operator, you pop out the last 2 elements from the stack, top 2 elements from the stack, do the operation and do a push operation. So, every operator you see, if it is a binary operation, you do 2 pop and 1 push, first 2 are pops and then with those outputs of the 2 pops you do the operation and then do the. So, that is what you see. Now, next what I see is a 5. Okay. So, this is removed because now the result is only 9. So, I have changed that and now you see a 5. So, just push it onto the stack. Next you see a 5, push it onto the stack. Next you see a 6, push it onto the stack. Next what you see is a thing. What will happen? You have to pop the 2, the result you have to push onto the stack. So, that is what will happen here, as I already explained. Pop 6 and 5 of the stack, do the operation multiplication and push the result onto the stack. Now, next you will see again what you see is an operation. So, what happens? These 2 are operated using the plus sign. So, that is what I do here. So, this 5 6 resulted in this. Now, this 30 and this 5 are added together. So, I get 35. Okay. Then I have this 8. Okay. Then I have this multiplication where 35 into 8 is done. So, pop 8 and 35, that was what on the stack. No? So, you pop those two, do the operation, put it back onto the stack. Now, what I encounter is again a minus. So, I have to minus 280 and 9. So, pop the 2 elements, minus it and put the result here. So, now where am I? I am here. Now, I have to I see an operand, I push it onto the stack, both together I have just done. So, 6 and 8, and then I see a multiplication. So, I have to multiply it. So, multiply it and put the result on the stack. Now, I see a plus. So, whatever is the last top two elements, I have to do the operation plus. So, that is what I will do, and then I again have a plus. So, I take the last two elements of the stack, that is these two, and do the operation. So, I get this, and so pop to -2 then 3 off the stack, do the operation and push the result onto the stack. Now, if the result -220 is at the bottom of the stack, and that is my result. But remember, if the stack is not I mean it should have only this result. If it has more than this result, there is something wrong in your equation. So, what we have done here is we have not done any other operation, we have just scanned the input, done either a push operation if you see an operand, or if it is a binary operator, you see an operator, you do 2 pushes, 2 pops, 1 push, 2 pops, 1 push. You keep doing this, you do not have any other logic, you just keep on doing this, and if at the end of the whole operation you get at the bottom the result, only only the one element should be there on the stack, and that is the result. If you have more than that, then there is something wrong with the equation. So, this is the evaluation of a postfix expression. You would see that this is so implementable using a computer. You have a small simple program and you have a stack, you can implement the evaluation of a postfix expression. You do not need to know what is open parenthesis, you do not need to know the precedence, you do not need to know anything. So, what we have done here is this is very important. As you can see, these elements are removed one by one, and I have actually done it in such a way that you can follow it. So, this is the operation of these two, this is the operation of these two, this is the operation of this, and whatever is on the top of the stack, which would have been a 5 that was there. So, that is this, then this is the operation of the last two, and so on. So, this is what we were doing. So, what we have done up to this point is we have said that algebraic expression, we have dedicated a complete module to remember, this is just an application of stack, and algebraic expression is what we were thinking about, and we have looked at how to convert an infix expression, which is the normal expression that we write it in programming languages and all that, convert it into a postfix expression, and then evaluated the postfix expression. The computer way of evaluating an expression is using postfix and a stack. So, that is why we say it is an inherent part of that computer application that we are using this stack for. So, we have used stack in both the places. Prefix to postfix, infix to prefix is a little more complicated, because we have to use 2 stacks for that. We are not going to look into that in detail. I leave it to you as a homework, because the order in which the operators and operands come is different. Otherwise, it is the same, but it requires the use of 2 stacks. And so, in this chapter we have discussed some important applications of stack. In fact, we have just taken one small area called algebraic expression and looked at how stacks can be used for this. What I want to stress again is the natural way in which stacks are used in a number of applications, because of the logic required. So, we outlined the conversion of infix to postfix, and we used a running example to explain that. Though I did not actually give you a table of in-stack precedence and incoming precedence, I explained it via an example, and I discussed the evaluation of a postfix expression using stacks, where we saw that just a simple operations. So, now from the result of this, you would have seen 2 different stack ADTs. Okay. What were the 2 different stack ADTs? One stack ADT required create a stack, a push and a pop. Okay. Now, this is where the indigeneity of the ADT operation comes. Now, in ADT stack, for evaluation of an expression, postfix expression, instead of using the basic operations which we already know, create, push and pop, I could use create stack, and that 2 pops and a push I could incorporate into a single operation, and then I can have a push, okay, separate push. Now, that would be a different ADT, a special ADT designed, stack ADT designed for the evaluation. So, that is how this becomes a little bit interesting. So, we will look at some other interesting applications of stack in the next module. So, thank you.